Oh, well, welcome back, everybody. So I hope the year started well for all of you. This is the first talk of the new semester for us. And Charlotte Aten from University of Rochester is going to talk about Orientable smooth manifolds, that they are essentially quasi-groups. Please, Charlotte, whenever you're ready.
So I did check this before, but just to double check. So can people all see my slide and where I'm writing PALS in white here? Okay, fantastic. So yes, thanks again for having me, especially since it's currently an important time in my career. I'm still in the process of applying to my, hopefully my first postdoc here. And I'm also honored to, for the second year in a row, give the first talk for PALS for the calendar year. This year, I'm talking about how orientable smooth manifolds are essentially quasi-groups. And I will admit that this is a little bit of a dramatic title for the talk in the paper, but I will explain what I mean in much more detail. And at the very least, hopefully you will see that there is a very close relationship between orientable smooth manifolds and quasi-groups. So, let's see. I'm gonna try to drag my annotation menu over here. Okay, fantastic. So, in the mid-2010s, Mark Herman and John Pakianathan, who is actually both my advisor and also Semen Yu's advisor, with whom this is joint work. So these two introduced a functorial construction of closed surfaces from non-commutative finite groups. And so the closed surfaces, remember, are the two-dimensional orientable manifolds that are like the two-sphere or the torus, or in general, the n-hold torus, of which it's traditional to draw perhaps this example. So they gave some construction which produced from a given non-commutative finite group some closed surface like these. So Semen Yu and I decided to produce an n-dimensional generalization of this. And there were two main challenges in doing the n-dimensional version. So the first was finding an appropriate analog of non-commutative groups. And the second was in desingularizing the n-dimensional pseudomanifolds, which arose at the first stage of our construction. Because really, although this isn't a direction we ended up pursuing, sort of the most fundamental construction from which our two functors that I'd like to talk about later are built is actually a construction of pseudomanifolds from quasi-groups. But I don't know as much algebraic geometry as I probably should, so we didn't really pursue the pseudomanifold perspective. Well, in any case, we did ultimately find that every orientable triangulable topological manifold could be manufactured in the manner that we described. And so perhaps it's a little too much to say that every orientable smooth manifold is a quasi-group in any sense. But at the very least, it is actually possible to use a single functorial construction to produce all homeomorphism classes of orientable triangulable manifolds. So that's what I hope to get to near the end of this talk, is a description of that construction. Oh, and please feel free to interrupt me if you have any questions. I'm hoping that this will go a bit better than the version of this talk which I gave at Binghamton's graduate conference in algebra and topology last semester, where I spent a lot of time giving more background because I couldn't assume that people knew universal algebra, but feel free still to ask me if you have any questions about anything during the course of the talk. Okay, so first I'll discuss Herman and Pakianathan's construction, and then I will spend quite a while talking about quasi-groups, And then I will take hopefully a little bit less time to talk about our two functors, which we called open serenation and serenation. And then finally, I'll talk about the relationship that all of this has with the Evans conjecture on the completion of partial Latin squares, and with our problem or conjecture on Latin cubes. So I'll discuss Herman and Pakianathan's construction just by giving an example of the construction without the full details, because in the subsequent section, I'm going to describe a generalization in full detail, well, more full detail. First of all, consider the quaternion group G of order 8, which consists of plus or minus 1, I, J, and K from the quaternions. So we would like to pick out all pairs of elements X and Y in G so that X, Y is not equal to YX, or in other words, X and Y don't commute. And we'll call this collection NCT for non-commuting tuples of G in anticipation of what is to come. They won't just be pairs in the future, but for now they are. We'll then define in of G, as in the input elements of G for our construction, to be all of the elements which appear in some non-commuting pair. In other words, in of G is just all of the non-central elements of the group G, which in this case is the quaternion group. Similarly, we'll define out of G to be all of the members of G which are the product of two non-commuting elements of the group. And these names will make sense in a moment. So in this example, we have that the non-commuting tuples or pairs from G just consist of all pairs of elements plus or minus U plus or minus V, where U and V are distinct elements of the set I, J, K. And so from that, it follows that the input and output elements of G are just all of the elements other than plus or minus 1, because each of I, J, and K fails to commute with something, and then the products of things that don't commute can give you any of plus or minus I, J, and K. So from this data, we can actually build a simplicial complex, which turns out to be a two pseudomanifold. I won't actually define pseudomanifolds in this talk, but basically they're things that look like n-dimensional manifolds, triangulated n-dimensional manifolds, where there can be singularities at the n-2 skeleton and lower, but if you only look at each n-1 face, at each codimension 1 face, then that has exactly two n faces on it. So for the two-dimensional version, that would be that if I look at each edge, there are exactly two triangular faces that meet at that edge. But if I look at a vertex, it's possible that a neighborhood of that vertex is not Euclidean, because, for example, there could be a whole sheet of triangular faces at this vertex, but then glued to that same vertex, there could be another sheet where this point and this point are glued together, and these are cycles around the same vertex. So we form such a simplicial complex where each of these two-dimensional faces in this example would be an input, so an input vertex, X, with this underlying decoration under it. So perhaps, for example, I with an underline under it to indicate it's an input vertex, and then another one which doesn't commute with it because we want X and Y to not commute. So say J with an underline under it to indicate that it's an input vertex, and then we would have the product of these, so I and J make K, with an overline over it to indicate that it's an output type vertex. So we want to distinguish between inputs and outputs. So I with an underline is not the same as I with an overline. And I also want to emphasize that this overline is just a decoration. It's not a conjugate or something like that. Okay, so if we do this, then we will obtain some simplicial complex whose facets are all of that form. And one sheet of the complex that I was just discussing is pictured below. And so now here, if we look at I underline, J underline, and K overline, so if we look at this face, that's the one I was drawing before, and this has a sort of natural orientation going from the left input to the right input to the output vertex. And so if I draw that orientation, I can see that I get an entire oriented face because j times minus I is k, and then minus I times minus j is k, and then minus j times I is also k. And so this is sort of a closed sheet, which we can envision as being perhaps a hemispherical cap like this, where around the boundary of this we have our input vertices I, j, and so forth. And then at the North Pole here, we have our output vertex k. So the entire complex consists of copies of things that look like this, somehow glued together. So there are 3 4 cycles in the sense of 4 cycle in a graph in the one skeleton of this complex, and each carry an octahedron on it. So like the hemispherical cap that I drew before, where this was the input vertex I, this was the input vertex j, and so on and so forth. So if we followed that around in one orientation, all of the products spat out k. But if we go in the opposite orientation, j times I is minus k, and then I times minus j, I times minus j will be minus k, and so forth. And so what we get is another hemispherical cap, but this one has at the South Pole minus k as an output vertex. And so together these two form a sphere or an octahedron. And now, so now if we look at this, this graph here is depicting part of the one skeleton of this simplicial complex. And then for each of these 4 cycles in this graph, ij, minus I, minus j, and so forth, each one of those has an octahedron carried on it in the manner which I just drew on the right-hand side here. So this is definitely not a triangulated 2-dimensional manifold, because if you look at any of these vertices, for example, the neighborhood of that vertex is not going to be Euclidean. It's not going to be homeomorphic to an open set in our tail. But it is a pseudo-manifold in the manner that I sort of vaguely described before. So it's at least close. If I only look at the edges, it looks at the interior of the edges, it looks like a manifold there. So this simplicial complex, which we'll call sim of G, or the simplicization of G, and Herman and Pakianathan just called X of Q8 for the 8-element quaternion group. This consists of 3 two-spheres, each pair of which is glued at 2 points, which are the vertices, the non-Euclidean points that are the vertices I was discussing before. So if we delete these points, we'll get a collection of punctured spheres, 3 punctured spheres. And then if we fill in the resulting holes, we'll get a manifold, which we'll call the Serenation of G, and Herman and Pakianathan just called Y of this 8-element quaternion group in this case. And so in this case, the Serenation of G is the disjoint union of 3 two-spheres. And so that deleting the non-Euclidean points and then filling in the holes was this desingularization process, which I had mentioned before. So that's the basic idea of Herman and Pakianathan's construction. And now I'd like to talk about quasigroups so that I can get us prepared to discuss the manufacture of n-dimensional pseudomanifolds, manifolds, and so forth. So, well, a binary quasigroup is a magma, so a set equipped with a binary operation, where if I fix any 2 of the variables x, y, and z to have some particular value in the universe A, then the equation f of x, y equals z has a unique solution. So this is also to say that a quasigroup is a magma, or a binar, in other words, or groupoid in the universal algebra sense, whose Cayley table is a Latin square, where each entry occurs exactly once in each row and each column. So all groups are, of course, quasigroups, but quasigroups need not have identities or be associative. So for example, the midpoint operation, taking the average of 2 points, say in Rn, That's a quasi-group operation. So is equipping the integers with subtraction. That's another quasi-group operation. And we can also define quasi-groups instead by this collection of identities, where we think of quasi-groups as being equipped with a binary multiplication f, and then two binary division operations, which I've called G1 and G2 here, which act like dividing on the left or the right side by an element. And so quasi-groups are also actually a variety of algebras, even though that previous combinatorial definition didn't seem to be defined in terms of universally quantified equations. Okay, so I'm hoping that's relatively familiar to people, or at least you can just accept that this is some variety of algebras with three basic binary operations. So, okay, so yes, this is all to say that, so I'm gonna write quas2 for the the class of binary quasi-groups. This is all to say that that is a variety of algebras. And so we have, of course, a nice category, and that's closed under taking quotients of algebras and products. And I want us to notice that I gave an example using the quaternion group before, but Herman and Pakianathan's construction works just fine with non-commutative quasi-groups, just the same way it would with groups. I didn't use anything special about, you know, groups having identities or multiplication or an associative multiplication in order to perform that construction. So we would like an n-ary version of a quasi-group for our n-dimensional generalization. So an n quasi-group or an n-ary quasi-group is a magma. So a set with a single n-ary operation, which I'll call an n-magma, although I know that isn't entirely standard, where if I fix any n-1 of the variables x1 through xn or y, then this equation, f of x1 through xn equals y, has a unique solution. And so this is exactly the n-ary analog of the combinatorial definition that I gave before of a binary quasi-group. Or in other words, an n quasi-group is an n-magma whose multiplication or Cayley table is a Latin n cube. And all n-ary groups are quasi-groups, but quasi-groups don't need to be associative in the n-ary sense. And that's actually going to be quite important for us because it'll turn out that n-ary groups aren't very helpful in our construction. So we do also have, though, that for any group G, the n-ary multiplication, where I just say that I should take the product associated however you want of the elements x1 through xn in G, that is a quasi-group operation on G. It's even an n-ary group operation on G, I believe, but that's, again, not going to be too helpful for us, it turns out. So similarly to the definition in terms of three binary operations I gave before for quasi-groups, we can also define an n quasi-group as an algebra with n+1 n-ary operations, which satisfy similar identities to those that I listed previously. And basically, each of these other n operations, these GI, are like taking this last argument y and dividing it simultaneously in each position except for the ith by the corresponding element xj. And so that might take a minute to unravel, but if you look in the binary case, this is actually exactly what we had before, and it does correspond directly to the combinatorial definition I also gave above. If you just have the multiplication operation f, these GIs are uniquely determined, and of course you can always forget them and then just get the operation f. So okay, so then we actually don't just want to use any n quasi-group operation, though. We need a certain special sub-variety of the variety of n quasi-groups. So we'll say that an n quasi-group is commutative when you can use any element of, so perm n is my notation for the just the symmetric group and n letters, the permutation group of 1, 2 up through n. So if I take any permutation and permute the entries that are being applied, that f is being applied to, if I get the same element all the time, then that's what I mean by a commutative n quasigroup. So any permutation of the arguments won't change the value of f. So an n quasigroup is alternating when instead permuting the arguments that f is being applied to by an element of the alternating group, so only even permutations, if that leaves f fixed, but switching two elements, just exactly two elements, or in other words, applying an odd permutation might change the value, that's what I mean by an alternating n quasigroup. And so, as you might notice, these conditions are both actually defined by universally quantified equations. They are actually specifying varieties of algebras. If you just write out what all of these conditions mean for every element, you'll see that these are identities, collections of identities. So our correct analog of the variety of groups will be the variety, which I'll denote AQN, of alternating n-ary quasigroups. And so the alternating binary quasigroups are just the quasigroups, because when n is 2, there are many interesting even permutations. So, okay, so that's the variety that I'm interested in. And the reason for that is basically the following picture. If I have, if I want to define a ternary operation that gives me a nice complex, I would like to have 3 inputs, say x1 is an input, x2 is an input, and x3 is an input. Similar to how I had defined that 2-dimensional simplicial complex before, I'd now like this 2-dimensional face to be a codimension 1 face in a 3-dimensional simplicial complex. Now the issue is that if I don't have any constraints on these elements x1, x2, and x3, I can actually define 6 different possible outputs, which would be f of x1, x2, and x3, or any other permutation. So f of x2, x1, x3, and so on and so forth. But this causes me a problem because I would like to at least get a pseudo-manifold, which means each n-1 face, so in other words, for each 2-dimensional face here, I'd like for it to only, I'd like for exactly 2 3 faces to meet at this 2 phase. And so having 6 possible outputs is too many. I only want at most, or I want to have at most 2 possible outputs. And for a non-commuting triple, I'd like to have exactly 2 possible outputs. So instead, I should say that all of the, if I apply the multiplication operation for my quasigroup to any even permutation of of x1, x2, and x3, I should get the same value, and that'll be one of my output vertices. And then if I apply f to any odd permutation of x1, x2, and x3, I should get a different vertex. So say x2, x1, x3. And then I will have a class of algebras which always make this occur, or it'll be the case that x1, x2, and x3 commute in the sense of this definition, and then I just won't include those in my complex. All right, so are there any questions about the motivation for using this alternating identity or class of identities? Okay. Again, please stop me if there are any questions. All right. So there are non-trivial members of this variety. It's not a trivial variety, but the easiest examples are either commutative, like the n-ary multiplication for an abelian group. That certainly works because anything that's commutative will fortiori be alternating. Or infinite. We can take the free alternating quasigroups, but those are going to be infinite, and we will actually need those later, but they're too much right now. So so Simon, you and I found the following example very tediously by hand. We took our universe to be actually z mod 5z, and we defined the following rather this is really a rather ad hoc construction. We took S to be the set of triples, ordered triples from Z mod 5Z, and then we defined an action of the cyclic group Z mod 5Z, the direct product of that with the alternating group on 3 letters. We defined an action of this group on S in the following way. So K, the pair K sigma, so an element of Z mod 5Z and an even permutation act on X1, X2, X3 by permuting the entries and then adding K to each component mod 5. So there are 7 members of the set. There are 7 orbits of the set of triples under this action, and 1 system of representatives is given here. So what we did is we had realized that we couldn't come up with non-trivial examples of ternary alternating quasigroups, as in not commutative examples. If we had a universe which had less than 5 elements, it was pretty clear quickly that 2, 3, and 4 elements were not going to do it for us. So we wanted 5, and we made an assumption that we would have this sort of symmetry of Z mod 5Z acting on itself. So we found that we had these orbits, and then we really did essentially just try choosing values for each of the orbits in a way that wasn't yet forbidden by the conditions we already had until we were able to produce an operation. And it wasn't clear that this could even be generalized to other modulus other than 5. So what we ended up finding was that if we define the operation F on the orbit representatives to be this, and then assume that F is equivariant with respect to the action of Z mod 5. In other words, if F of 0, 0, 0 is 0, then F of 1, 1, 1 is 1, and so on and so forth. Then these choices of values for the orbit representatives determine an a ternary alternating quasigroup operation. And so there's no reason that I can see, or that we could see back then, that this should generalize to some other more general construction. It seemed to be quite ad hoc. I can't explain to you why the correct choices were 3, 4, 4, and 2 here. So I apologize for that. But we do have an example of a non-commutative order 5 alternating ternary quasigroup. And so, of course, by taking products of this thing with itself, we can get infinitely many finite non-commutative alternating ternary quasigroups. And so we do have infinitely many finite examples. So we actually reached out to Jonathan Smith to see if anyone had studied the varieties of alternating N quasigroups before, because it seemed like something that people would have done already. And Jonathan Smith seemed like someone who would know if this had been done. But it seemed that nobody had. He didn't give us any references or anything. So he did, however, give us an example, which we generalized into an alternating product construction, which takes an n-ary commutative quasigroup and an n+1-ary commutative quasigroup and spits out an n-ary alternating quasigroup, which is typically not commutative. So that construction is the following. So if we have sets A and B, we say that a map from A to the N to B is an n-ary alternating map when its value is unchanged by even permutations of its arguments. And so the canonical example, indeed the example that was originally given to us, although he didn't phrase it quite this way. So the example that was originally given to us involved the determinant of an n by n matrix over some field. And of course, you want to take finite fields to give finite examples. Okay, so so in general, then the alternating product of an n+1-ary commutative quasigroup and an n-ary commutative quasigroup is the following. So we'll take the universe of our alternating product to just be the direct product of the universes. And then the alternating product of these two maps, G and H, the two basic operations of the quasigroups over this alternating map alpha, which is given, is defined in the following way. So first, just apply the n-ary operation G to the n elements u1, u2 up through un in the first coordinate. So in that coordinate, we're just doing what we would have in the direct product. So then the twisting by, or alternating by alpha occurs in the second component, where remember that H is n+1 array, so it needs to eat n+1 things, but we only are plugging in V1, V2 up through Vn, n things from V. So then the n+1st thing that we plug in is this alpha of U, and that's what gives us that. So this operation will be alternating but not commutative when this alternating map alpha is alternating but not commutative in the obvious sense. Okay. So this might look familiar to people. I'm not entirely sure how familiar, but first of all, I would like you to notice that the variety of n quasi-groups, just not necessarily alternating, just the variety of n quasi-groups is congruence permutable and hence congruence modular. I don't know if this is actually something that anyone has ever written down or published before, but in our preprint, which I can link you if you haven't already found on the archive, we do give a Maltsev term for the variety of n quasi-groups, just in case nobody bothered to write it down before. But in any case, the variety of alternating n quasi-groups is then also congruence modular. And although I actually don't know about this as much myself as I should probably, but it turns out that in any congruence modular variety, it's possible to decompose some algebra into this sort of twisted product of an abelian algebra Q and this algebra B, which is A mod its center. And so at least this looks somewhat similar, and may in fact actually be the same thing, although I'm not entirely sure myself yet. I'd also like to note the similarity between this construction and the factor set construction of group extensions with an abelian kernel. This also is, this construction of the alternating product construction I just discussed is actually a generalization of that. I think it is a direct generalization of that. But okay, so it's similar to lots of things. Now, I'd like to discuss some of the last notation I need before I can actually give our construction of n pseudo-manifolds and manifolds from alternating n-ary quasi-groups. So similar to what I did in the example from Herman and Pakianathan's paper, we're going to say that a tuple A1 through AN commutes in a given n-ary alternating quasi-group when actually permuting its arguments by any permutation, including an odd one, will give you the same value for their n-ary product. So then similarly, I would like to define the collection of all non-commuting n tuples from an n-ary quasi-group A, n-ary alternating quasi-group A, to be the collection of all n tuples which do not commute in A. In other words, those are the n tuples, like say the triples, if we're in the n=3 case, where there would be exactly two possible output vertices assigned to each, assigned to such a triple of input vertices x1, x2, and x3, like I had before. So if these guys are non-commuting, then we should get exactly two different outputs, which will again essentially be their ternary product under an even permutation, given some pre-assigned ordering, and an odd permutation. Okay. So I'd also like to talk about homomorphisms a little bit, since that's, of course, always very relevant in universal algebra. Homomorphism of alternating quasi-groups is said to be an NC homomorphism, or non-commuting homomorphism, when it preserves the collection of non-commuting tuples for the quasi-groups. In other words, if A doesn't commute in A1, then H of A should not commute in A2. And so if you think about what this means in the case that A is actually a binary group, that's saying that the kernel of this homomorphism should be a subgroup that is contained in the center of the original, of this first group, A1. And so it's tempting to say that the NC congruences, in other words, the kernels of these homomorphisms of A, should be those contained in the center of A, in the universal algebra sense of the center of an algebra. But we weren't actually sure whether this is the case. And so this is another area where if I knew universal algebra better, I might be able to prove or disprove that conjecture. And I would appreciate any feedback on this, of course. But okay, so now if there are no more questions, or if there are no questions or comments, I would like to talk about our first function, our first functor, which is the open Serenation functor. So this is a functor which takes this category NCAQN. So this is the category whose objects are alternating quasigroups and whose homomorphisms are only the NC homomorphisms. So it's not actually the whole variety of alternating quasigroups in the sense of that being a category. It's the subcategory which still has all of the objects but only has NC homomorphisms as the morphisms. So if we restrict to just those morphisms, we have a functor which we'll call the open Serenation from that category to the category of smooth and manifolds. And another sort of side comment, our manifolds are all allowed to not be second countable, but they should be disjoint unions, possibly uncountable disjoint unions of second countable connected components. So if you're worried that, what if I take a very large cardinality quasigroup, how can I possibly get a manifold? That's what I mean by a manifold here. It's not entirely standard, but okay. So in order to do this, first we're going to define that simplicization functor that I mentioned before, where we start off with our alternating quasigroup and we produce a simplicial complex in the manner that I've drawn pictures of already in the 2- and 3-dimensional cases. So we're going to define the input and output vertices analogous to those that I defined before. The inputs are all of the entries in non-commuting tuples of A, and the outputs are all of the n-ary products of non-commuting tuples of A. So equipped with those, we can then define the set of vertices of the simplicization of A to be all of the input vertices decorated with an underline, and then all of the output vertices decorated with an overline. And so this will disjointize these two sets if they were to have some little a in common. And then the faces of this simplicial complex are going to be like those that I already drew before. They'll have the n input vertices from a non-commuting tuple, and then the n plus first vertex will be the n-ary product of those labeled with an overline to separate it and indicate that it's an output. And so the simplicial complex, sim n of A, is the simplicial complex of those vertices and those faces. Oh, and of course, when I said faces, the faces were these before, really I meant that these are the facets, the highest dimensional faces, and then by this I mean the power set. So of course I want to take all subsets of those to obtain an abstract simplicial complex. Okay. And then we can do something similar with the morphisms, and that's why it was important to require that they preserve non-commuting tuples so that we could get simplicial maps, but I'm not going to discuss that in detail at the moment. So that was only the first step in order to create this open Serenation functor though. So at this point, we actually have that this sim A is actually, again, an n-dimensional pseudo-manifold. If I look at any n-1 face, that's a place where exactly two different n faces meet. But there might be other singularities in the n-2 skeleton that make this not actually a triangulated n-manifold. So if we want to get an actual manifold, what we can do is we can take the open geometric realization of this pseudo-manifold sim A. And by that, I mean basically take everything except for the n-2 skeleton of the simplicial complex and geometrically realize that. There's a canonical smooth atlas that you can equip this thing with. And I will describe that a little bit, although I wouldn't be described if someone who knows geometry much better than me already knows how to do this and has published it somewhere. I just couldn't find it. So the idea is that if you have two faces meeting in this simplicial complex, then so I'll draw the two-dimensional version here. So we have two triangles meeting in a two-dimensional simplicial complex so constructed. Then what I would like to do is only look at the interiors of these two faces and then the interior of the edge between them. So in other words, just not the vertices in this case. So then the open bipyramid in the two-dimensional case would just be like the interior of these two triangles and then the one face in between them. In general, it would be the interior of two n simplices that meet at an n-1 face, and we're not including anything that's not in the interior of those three simplices. Okay, so we have a standard open bipyramid in Rn that we use to define our charts. And by taking that as our domain, we can define a collection of input type charts, which we'll denote by phi underline sub A for some non-commuting tuple A. And basically what these are doing is they are taking this open bipyramid, they're making one unit basis vector, say in R2 in this picture, to be, say, oh, I guess I called it U1 here, another one to be U2, and then these two other vertices will be the two different products of U1 and U2. So this, say, will be F of U1, U2, and then this will be F of U2, U1. And you can do a similar thing in n dimensions, and that's what is being defined here. It's the n-dimensional version of that. So you can do a similar thing for, there are similar charts for output type, which are just defined similarly, and you need those to cover the entire space in charts so that you can have a manifold or an atlas. And so the open serenation of the quasi-group A is then the open geometric realization of that simplicization of A. So it's essentially the geometric realization of the n-2 skeleton of that pseudo-manifold equipped with the atlas that I just somewhat described. And so to give you an idea of what these things can look like, if I take the ternary quasi-group A that I gave before, the ad hoc example of order 5, this graph depicts this is the incidence graph of the three-dimensional facets of that three-dimensional simplicial complex. So each one has 4 faces, so that's why it's a 4 regular graph. They're labeled by the triple of input type vertices, which remember are members of Z mod 5. This is the one skeleton of the same simplicial complex. So we have that. And one may verify that the open serenation is a 3-sphere minus the graph that is pictured previously, which is homotopy equivalent to the wedge sum of 21 circles. We've given some type of smooth manifold structure on that thing coming from this quasi-group. Now, to form the final functor serenation, which I would like to talk about in the next, I have 7 minutes, right? I should finish by 50. Okay. So in order to produce this functor, basically what we would like to do is take the preceding manifold, which which is some smooth manifold, but it turns out to not be too exciting in the sense that, although I won't describe it at all here, a deformation retracts to a one-dimensional graph. We can make a more exciting manifold, though, if we equip the open serenation with a Riemannian metric, which we can actually do in a functorial manner, whoops, and then take a certain metric completion of it. So basically this metric that we would like to equip the open serenation with is the one that makes all of the simplices into regular simplices whose edge lengths are all the square root of 2. In other words, if you take the standard simplex in Rn, or Rn plus 1, so the standard n simplex in Rn plus 1, then we would like all of our simplices to have the geometry of that thing. So that's possible to do. You can see it in the paper. And then we would like to form the metric completion of this space, not the usual metric completion, but the metric completion where we take only those points which would be locally Euclidean in the standard metric completion. So usually when you take the metric completion of a Riemannian manifold, you'll get something which is not a manifold anymore. It has singular points. I would like to just ignore those singular points, just throw them out. So if we do that, we can define our Serenation functor, which takes an alternating n-ary quasigroup and spits out this Euclidean metric completion of the open Serenation of the quasigroup with respect to the standard metric that I just vaguely described. And so if we do that in the previous example of that ternary quasigroup we started off with in the beginning, the Serenation of that quasigroup is just the 3-sphere. However, notice that the Serenation is only a topological manifold, whereas the open Serenation could actually be equipped with the structure of a smooth Riemannian manifold. The advantage is that that smooth Riemannian manifold was just, up to homotopy was just a graph, but the Serenation can be something more complicated, like the 3-sphere. So naturally, the first question, I guess, is that you might ask about these things is, what manifolds can you actually make in this way? And so we'll say that a connected orientable n-manifold is serene when there's some alternating n quasigroup A, so that M is actually a connected component of the Serenation of A. It's too much to ask that M should actually be the Serenation of a quasigroup, probably. So at least let's see if we can find every manifold as a connected component of one of these guys. And so our theorem is that every connected orientable and triangulable n-manifold is serene. And I only have a few minutes left, so I will say, I guess very quickly, just like I did in the previous talk, I guess I took too long discussing quasigroups, but it was fun, that basically what we want to do is consider a triangulation of the given manifold M, so say this one, and what I would like to do is then subdivide each of the facets so that I can make a little sheet here. I'll take each of the vertices, say A1, A2, and A3 from the original manifold, and then I will use the orientation, because we should be given an orientation, to define an orientation on this little sheet. And then I'll declare that f of A1, A2 is this central vertex, which is the same thing as f of A2, A3, and that's the same thing as f of A3, A1. So it is indeed possible to write down the n-dimensional analog of that, and that is essentially giving a presentation for the alternating quasigroup that one would like to use. So, okay, so I know that was really quick, but I suppose we can discuss it in more detail if people have questions. But I would like to at least make a couple comments in the last 2 minutes, say, about Latin cubes.
Sorry, Charlotte, feel free to take 5 minutes still, so don't feel
okay. Well, okay, so I hope that wasn't too rushed, but I did want to mention the connection with the Evans conjecture and Latin cubes, so I suppose I'll take the next few minutes to do that. So suffice it to say, assuming that you believe that that construction that I just outlined works, then we do have a way of producing every triangulable, orientable, smooth manifold from some alternating n-ary quasigroup. However, those alternating quasigroups I just mentioned, I really just described how to produce a presentation of them. And in general, they'll be infinite, right? Typically, if you take a free algebra in any variety, I mean, okay, not literally any variety, but typically if you take a free algebra in some variety, it's probably going to be infinite. I know that isn't always the case, but right, the free group is certainly infinite, for example. And then quotients of those guys will still typically be infinite, right? You can't always expect that a presentation is going to give you a finite algebra. Okay, so it's natural to ask, well, regardless of what the output of that construction was that I just mentioned, is it possible to actually find every compact manifold, so one that could actually be triangulated by finitely many simplices? Is it possible to construct each of those using an alternating quasigroup which is actually finite? because then if we only cared about compact manifolds, we could just focus our search on finite alternating quasigroups, and we wouldn't have to worry about the intricacies of these infinite algebras. So we'll say that a connected, compact, orientable, smooth n-manifold is quasi-finite when there exists some finite alternating n quasigroup A, so that M is homeomorphic to a component of the serenation of A. And I want to emphasize here, just homeomorphic. There's nothing actually preserving the smooth structure here. I just am saying smooth here to guarantee triangulable, really. Then our question is every connected, compact, orientable, smooth manifold quasi-finite? Because then, regardless of that, construction that I gave before from our theorem, we would be able to say, well, you don't have to do that. You can just find this finite quasigroup that will allow you to construct your manifold for any such manifold. So in order to pose the relevant combinatorial question, whose answer would give us an answer to that topological question, I'd like to say that a partial Latin cube is some n+1 relation on a set A, where if I look at any position I, 1, 2, up through n, then there exists at most one AI, so that the tuple A1 up through AN+1 is in theta. In other words, theta looks like the graph of a partial quasigroup operation, partial n quasigroup operation. And so that would be a partial Latin n cube. And notice it's partial Latin n cube is an n+1 relation, and that's because the graph of an n operation is an n+1 relation. So Evans conjectured that each partial Latin square, that's a partial Latin cube with, so theta is a partial Latin cube for n equals 2, so which would be a ternary relation. Evans conjectured that each partial Latin square with, which has an underlying set of size, okay, this should be n. Sorry, I'm switching the meaning of n here. So if the size of the underlying set is n, and the size of the relation is n-1, in other words, at most n-1 spots on the Latin square table are filled in, then Evans conjectured that the rest of the table could be filled in to obtain a complete Latin square, in the sense that all of the places in the Cayley table of the operation are filled in, so to speak. And so this was proven true by Smetaniak, and I'm not sure how to pronounce that, in 1981. And similar results are known for special classes of higher dimensional Latin cubes. And tantalizingly, those classes are actually usually varieties of higher arity quasigroups, although sadly not alternating quasigroups to my knowledge. So, okay, so then a complete Latin n cube would be the graph of an n quasigroup operation, as I mentioned. And we'll say that a partial Latin n cube is alternating when, if we take an even permutation of the first n elements of a tuple that belongs to our partial Latin n cube, then we get another member of the partial Latin n cube with the same same n plus first coordinate, which is essentially saying that a partial Latin n cube is one which obeys the alternating identities when the corresponding compositions are defined. Or in other words, it's a partial alternating n quasigroup operation. So if we have a finite partial alternating Latin cube, does there always exist some finite complete alternating Latin cube which contains it? Or in other words, can you finish the partial alternating Latin or partial alternating n quasigroup operation to actually obtain a finite n quasigroup operation, which is still alternating? And that's kind of the hard part, I guess. And so this is a slightly weaker question or conjecture than the Evans conjecture, because we're not even asking that you have n-1 entries of an order n table filled in. you could add 100 trillion entries if you need to complete your alternating Latin cube. We just would like to know if it's possible to always do this by only adding finitely many entries. And so I'd like to note that since the Evans conjecture is true, and that's stronger than the n=2 case of our question, we have this corollary of the Evans conjecture, which is that every connected compact orientable surface is a component of the serenation of some finite binary quasigroup. So in other words, it is actually always possible to perform our construction, or in other words, the generalization of Herman and Pakianathan's construction for quasigroups instead of just groups. And no matter what connected compact orientable surface you have, it is always possible to find some finite quasigroup whose serenation is that surface. So this is not something that's known to be true for groups. It's not known whether or not any group would be enough to get any compact orientable surface, but this is actually a relatively easy corollary of the Evans conjecture if we allow ourselves to use non-associative quasigroups. All right, well, here's the original paper. Obviously there are lots more references in there. I can give you more if you would like. Yes, and thank you so much for having me here today.
Thank you.